Hello everyone, I am Dr.Rajeshwari, Assistant Professor in Computer Science. In this video, we are going to study about data representation. Data means what? The data is nothing but a fact. The data what we give to the computer. The data is in the form of numbers or characters. Let us see how this human readable data is represented and processed into machine readable form in digital systems. And also we shall study about significance of different number system representing the data in a digital system. Data representation. Having knowledge of what is data, what's information, and how computer works, and also binary numbers. What are these binary numbers? Binary means 0 and 1. Nothing but a machine language. Computers work in binary. Text, numbers or symbols are represented in the form of zeros and 1. Why? We humans work with decimal numbers, that is 0 to 9. We like decimal number system because we have 10 fingers, which makes us easy to count. Machines, on the other hand, cannot implement 10 different voltages to represent decimal number system in a digital equipment. So only many number systems have been evolved, but the easiest way to give instruction is on and off. On represents 1 and off represents 0. These 0 and 1 are called as bits. Computers have thousands, millions of electronic switches called transistors. Since transistors store binary information on signal state, that is 1, and off signal state, that is 0. So only text, numbers, symbols are represented as a combinations of zeros and 1, which computers can understand. These are the topics we are going to study: data representation, the number system. We have different number system, that is a decimal number system, binary number system, octal and hexadecimal number system, and their conversions. And also we will discuss about character representation. Data representation means there are two basic types of data processed by computers. What are those? Characters and numbers. You might be curious that how these characters and numbers are represented as a binary data, that is 0 and 1, internally inside a computer, because computer can understand binary number system, because since it has an electronic components in a digital computers which operates in a binary mode, zeros and ones. Let's move to the number system. Numbers means what? Are the symbols, where each symbol represents certain values, and this number system is represented using distinct symbols. We have two types of number systems: non-positional number systems and positional number systems. Non-positional number systems means what? It also has different symbols to represent different values, but these type of number system do not have positions like units place, tenth place and 100th place. Example, Roman numbers. These Roman numbers have symbols like I is equal to 1, V is equal to 5, X is equal to 10, L is equal to 50, C is equal to 100 like this. Say for example, we have a number here, Roman number L, X, X. What is the value of this Roman number is? This can be found by adding their value. L means 50, X means 10. So when you add 50 plus 10 plus 10 plus 10, we got 80. So what is the value of this Roman number? Is nothing but 80. Then what are these positional number system? Which has positions like unit positions, 100 positions, 1000 positions. And these composite number depends on the value of the digits, the positional value of the digit, nothing but weights of this, and also the base of the number system. Let us move to the positional number systems. The first one, that is the decimal number system. Decimal number system is a positional number system. It has 10 symbols, that is 0 to 9. So the base of this decimal number system is 10. Base means total number of digits in a system. So the positional values are expressed as powers of 10. Say for example, consider an example, a decimal number 542.76. 542.76, 2 is in unit position, 4 is in 10th position, 5 is in 100th position. Numbers after this decimal point, that is 7 is in 1/10th position and 6 is in 100th position. Since numbers after this are represented as -1th place, -2th place like this. Express these as a powers of 10 because this is a decimal number system. So after this, multiply this number with their position. 5 into 10 square, 4 into 10 to the power of 1, 2 into 10 to the power of 0 plus 7 into 10 to the power of -1 and 6 into 10 to the power of -2. Finally, after calculating, we get a number that is 542.76. You can observe that each digit signifies different values depending on the position it occupies in the number. Binary number system is also a positional number system. It has two digits, that is 0 and 1. We call it as a bits. Since only 2, so the base is also 2. And positional values are expressed as a powers of 2 in a binary number system. Consider an example. This is one binary number. This is actually a binary number of a decimal number, that is a 27.625. So now express this one is in unit place, 10th place, 100, 1000 and then 10,000 like this. And these numbers after this decimal point are expressed as a -1th place, -2th place, -3rd place like this. And these are expressed as a powers of 2. Here you can see that sum of product of each digit with its positional value is done. Octal number system is also a positional number system. Digits in this octal number systems are 0 to 7. Total 8 digits are there. So the base is 8 and are expressed as a powers of 8. Consider an example, 234.56 and are expressed as a powers of 8. And to know the value are done with the sum of product of each digit with its positional value. Last, that is a hexadecimal number system, is also a positional number system. It has numbers, that is digits 0 to 9. After 9, it has a symbols, that is A, B, C, D, E, F, representing A representing 10, B 11, C 12, D 13, E 14 and F 15 respectively. So, the highest single digit number is F, having the value of 15. Since it has a total 16 digits, so the base is 16 and positional values are expressed as a powers of 16. Consider an example of hexadecimal number 5AF.70 and are expressed as a sum of product of each digit with its positional value. Conversions. Decimal to other number system, that is conversion from decimal to binary, decimal to octal or decimal to hexadecimal number system. This can be done by using a division method. To perform this, when you are converting decimal to other number system, the decimal number system is divided by the base of a target number system. I mean to say, when you are converting decimal to binary, the base of target number system is 2. So, this decimal number is divided by 2. When you are converting decimal to octal, base of octal number system is 8. So, the decimal number is divided by 8. In the same way, when you are converting decimal to hexadecimal, base of target number system is 60. So, the decimal number is divided by 60. First, divide the decimal number by the base of the target number system and note the remainder. Note the first remainder as least significant bit. Then, divide the quotient of previous division by the base and note the remainder. This is successively done till the quotient becomes 0. After that, note the last remainder as most significant bit. Then, collect the numbers from most significant bit to least significant bit. This I will show with an example. Consider a conversion decimal to binary. Here, consider a number, decimal number, that is 42. Convert this number 42 to binary number system. The target number system is binary. Base of binary is 2. So, divide this number 42 by 2. When you divide, you get the quotient as 21 and the remainder is 0. So, this first remainder is noted as LSB. Again, divide this quotient of previous division, that is 21 by 2. We get the quotient as 10. Remainder is 1. Note the remainder. Divide 10 by 2. Got the quotient as 5. Remainder is 0. Note the remainder. Divide the previous quotient, that is 5 by 2. 2 2s are 4. Remainder is 1. Note the remainder. Divide the 2 by 2. You got the quotient as 1 and the remainder, that is 0. And so on. Note the last remainder as most significant bit. Collect the numbers from most significant bit to least significant bit, that is numbers are 10, 10, 10 are the binary numbers. So, this is a binary equivalent of decimal number, that is 42. This is how to convert decimal to binary. Let us see few more examples. Decimal to binary. Number given here is decimal number is 12,345. Divide this 12,345 by 2 because the target number system is binary. Base of binary is 2, so divide it by 2. We got the remainder as 1. Note it as LSB. And divide the previous quotient, that is 6172, again by 2. Note the remainder. And so on till you get the quotient as 0. And note the last remainder as MSB. Collect the numbers from MSB to LSB. We get 11, 6 zeros, 111, 001, which is a binary equivalent of the decimal number 12,345. The same way, decimal to octal conversion. Here, the base of target conversion is, that is octal, that is 8. Divide the decimal number 12,345 by 8. We get quotient as 1,543. Remainder is 1. Note the remainder. Again, divide the quotient of previous division by 8. Note the remainder. And so on up to got the MSB as 3. And write the numbers from MSB to LSB, that is 30071. So, the octal equivalent of 12,345 is 30071. Convert decimal to hexadecimal. 12,345. Target conversion is hexa. The base of hexa is 16. Divide by 16. Note the remainder. First remainder as LSB. Last remainder as MSB. Write the numbers from MSB to LSB. We get 3039. See another example of hexa. Convert 725, that is decimal number, to hexa. Divide this and note the remainder. Divide by 16. We get the quotient as 45 and remainder as 5. LSB is 5 and MSB is 2. We have a number 13, which is actually a D in a hexadecimal number system. So this 13 is represented as a D. Write the numbers from MSB to LSB, that is 2D5. So hexadecimal equivalent of 725 is 2D5. Let's see conversion from other number system to decimal. That is other number system from decimal to means octal to decimal, binary to decimal, or hexadecimal to decimal. To perform this, a multiplication method is used. In this conversion, multiply each digit of the number with its corresponding weights and sum all the products of the step 1 to get the numbers in the decimal number system. This I'll explain with an example of binary to decimal conversion. In the last slide, we had converted a number, that is 42 to binary. We got the binary equivalent of decimal 42 as 1010. Now, we'll convert this binary to decimal. Let us see whether we get 42 or not. Consider this binary number. Convert this into decimal number system. So, write the number, that is binary 101010. This 0 is in unit place and this 1 is in 10th place and so on. Represent these in the as a powers of 2. So 0, 2 to the power of 0, 1, 2 to the power of 1 and so on. The last number, that is in 2 to the power of 5. Now multiply 1 into 2 to the power of 5 with their positions. That is 0 into 2 to the power of 0, 1 into 2 to the power of 1, 0 into 2 square, 1 into 2 cube, 0 into 2 to the power of 4, 1 into 2 to the power of 5. We get like this: 1 into 32, 0 into 16, plus 1 into 8, 0 into 4, 1 into 2, plus 0 into 2 to the power of 0, that is 1. When you perform sum, we get a number as 42, which is a decimal equivalent of a binary number. So here we have converted binary to decimal. We got the correct decimal number. Let's see some other examples. Here also we have one binary number. Write the this one is in unit place. So 1 into 2 to the power of 0. 0 is in 10 place. 0 into 2 to the power of 1. And so on. The last number is in 1 into 2 to the power of 7. Perform the multiplication and add the numbers. We get number as 217, which is a decimal equivalent of this given binary number. In the same way, let us convert octal to decimal. Here we have a fraction actually 345.6, which is in octal. Convert this into decimal. To perform this 5 is in unit place, so 8 to the power of 0. 4 is in 10th place, 8 to the power of 1. 3 is in 100th place, so 8 to the power of 2. Numbers after this decimal point are expressed as negatives, that is minus 1th place, so 6 into 8 to the power of minus 1. Perform the calculation. We get 229.75, that is a decimal equivalent of the given number, octal number 345.6. In the same way, hexadecimal to decimal. Here the hexadecimal number is given. You have to convert this into decimal. 5AF.D. This F is in unit place, hence written as a 16 to the power of 0. A is in 10th place, hence written as 16 to the power of 1. 5 is in 100th place, so it is written as 5 into 16 square. Number after this decimal point is minus 1th place, so it is written as D into 16 to the power of minus 1. Perform the calculations. We got the decimal equivalent of hexadecimal number is 1455.8125. This is how to convert other number system to decimal. Till now we have seen how the numbers are represented in a computer system. Numeric data is not the only data which is handled by a computer system. Besides numerical data, we often require to process alphabets. In alphabets, capital letters, small letters, special characters, punctuations, arithmetic operators, etc. So, let us discuss how these characters are represented in a binary form, that is, in terms of zeros and ones combinations. There are three widely used character codes, namely binary coded decimal BCD, extended binary coded decimal interchange code EBCDIC, American Standard Code for Information Interchange ASCII. Let us discuss one by one. Binary coded decimal. So this is a BCD code of 4-bit, means it consists of 4 bits. It can represent only 10 decimal numbers. In this chart you can see the binary equivalent of decimal numbers 0 to 9. This is one of the oldest method. In this number, the whole number is not used to convert by dividing it by 2. Instead, each number is converted into its binary equivalent. So, it can represent 10 decimal digits only, since it is a 4-bit BCD code. 4-bit means 2 to the power of 4. So 2 to the power of 4 means 16 combinations are possible from 4-bit BCD. But out of 16 combinations, it can represent only decimal numbers. Only 16 combinations are there. So this 4-bit BCD was insufficient to represent 26 alphabets and 28 special characters, because only 16 combinations are possible from 4-bit BCD. Hence, first 10 combinations are used to represent decimal numbers. Since 4-bit BCD was insufficient to represent the characters, 4-bit designers commonly use 6-bit BCD. 6-bit BCD means 2 to the power of 6 means 64 combinations are possible in 6-bit BCD. Out of the 64-bit combinations, first 10 combinations are used for represent decimal numbers, 26 for uppercase and another 26 for lowercase. Totally 62 combinations out of 62 are used, but still 6-bit BCD was insufficient to represent 28 plus special characters. Hence, researchers extended this 6-bit BCD to 8-bit BCD by adding 2 bits as additional zones. So the resulting coding system is called as Extended Binary Coded Decimal Interchange, that is EBCD IC. It uses a zoning method. Let us see how this is. So another most widely used EBCD IC. Here number of bits used is 8 bits. So 256 characters can be represented. Not only the alphabets, that is capital and small letter, 28 plus special characters. In addition to that, non-printable characters like printer vertical spacing, control characters, cursor movements, etc. In this chart, you can see the character representation of EBCD IC codes. And another widely used character system is ASCII code. ASCII code, it is the most widely used, and it uses 7 bits. It can represent 2 to the power of 7 means 128 characters. See here, ASCII are of 2 types, ASCII 7 and ASCII 8. ASCII 7 means 7-bit code. 2 to the power of 7 means 128 characters. ASCII 8 means 2 to the power of 8, that is, it can represent 250 different characters. ASCII representation of characters A, B, C, D up to Z, capital and small letters is shown in here.